Let's start with a simple calculation. If you take the numbers 1 through 9 and add them all together in a single line, what is the total? The sum is 45. This single number represents the total value we have to work with. Thousands of years ago, Chinese mathematicians took this simple linear addition and moved it into a two-dimensional grid, creating what we now call the magic square. Adding numbers in a straight line is one thing, but the task changes entirely when those same 9 values must balance across every row, column, and diagonal simultaneously. This is the environment, a 3x3 grid where the rules are absolute. Every horizontal row, every vertical column, and both diagonals must add up to the exact same total. That means 8 different pathways must reach equilibrium simultaneously. It's tempting to simply place the numbers in order, reading 1 through 9 across the rows, but the math doesn't hold. The top row adds up to 6, while the bottom row jumps to 24. The grid is completely lopsided. This grid is too interconnected for simple trial and error. To solve it, we have to look past the numbers and focus on the system. If we look at this empty base, we can deduce the rules of the board before placing a piece. We know our total is 45. Since that value must split evenly across 3 horizontal rows, each line must equal 15. Here we see the architecture of intersection. Because of how the grid is designed, some slots are more connected than others. The center space is unique. While other slots sit on 2 or 3 lines, this single point sits at the intersection of 4, a row, a column, and both diagonals. Because the center must help balance 4 different equations at once, it requires the most versatile number in the set, the 5. Understanding the geometry of the empty space is the first crucial step toward controlling the numbers that will fill it. We place the 5 in the center. It is now the pivot point for the entire board. To maintain 15, we balance extremes. If we place 9 on one side, it must be neutralized by our lowest value, the 1, on the exact opposite side. In this completed version, you can see that logic applied to the whole grid. Every high number is paired with a low number to keep the lines at 15. As this orange board shows, the internal harmony works regardless of the board's design. A moment of wonder. The square is no longer a random collection of digits, but a single interlocking ecosystem. While larger magic squares exist, this model offers a direct way to visualize mathematical balance. For most students, math has traditionally been a rigid experience, defined by static desk work and repetitive calculations. Abstract work on paper or a chalkboard carries a certain friction. There is a permanence to it, the fear of writing the wrong answer, and the chore of erasing it. But when a problem has physical weight and color, the mode of exploration changes. It turns calculation into tactile play. Being able to physically swap pieces removes the penalty of failure. It encourages a child to experiment and tweak their logic until the patterns emerge. The magic square isn't just a curiosity. It's an active tool for developing spatial logic and mathematical conversation. By manipulating physical pieces, children can see the math moving, rather than just solving for a variable in their heads. It proves that the rules and constraints of a problem are exactly what make the discovery of the solution rewarding. When we make the abstract tangible, we show that mathematics is a discoverable, perfectly balanced puzzle hidden just beneath the surface.